Let us do a couple more examples involving the parameter elimination technique. In example 3, let us say that we have to identify the curve by its parametric equation. And the parametric equation given here is x as a function of t equals to t squared, y is a function of t equals log t. And t here has to be positive. Obviously, we won't be able to plug in negative or 0t into the log here. So this is a natural restriction. So observe that here there are two ways to eliminate the parameter. So eliminating t can be done in two different ways. So one way would be to use the first equation to express t through x. So from x being equal to t squared, we have that t is equal to square root of x. And substituting into the second equation, we have y equals the log of square root of x. So if you wish to simplify this further, you can observe that this is log of the x to the 1/2, and so it is equal to 1/2 log x, because raising x to the power means you're multiplying the exponents that comes out of the logarithm. And so we have the equation y equals 1/2 log of x, with x being positive. So in other words, the curve that has this parametric equation is just the graph of the natural logarithm. Another way to think of this same curve is to solve the second equation for t. We have from y equal to log of t, it follows that if you take e and raise it to the two parts of this equation, we'll have e to the y equals to e to the log of t, and so this is just t. It follows that t is equal to e to the y. And then substitute. So this is the expression of t in terms of y, and then we can substitute into x equal to t squared, and in view of this expression for t, we have x equals to e to the y squared, or equivalently x equals e to the 2y. And so we have two different ways to think of this curve, of the curve with this parametric equation. It's either y is a function of x or x is a function of y. And depending on which dependence you're interested in, you can use the corresponding approach to solve for t. So let's think about this curve as a trajectory of a physical particle and try to determine the direction of motion of this particle. So we have that y is equal to 1/2 log of x. So the graph of that is something of this form. And so it has a single x-intercept at 1. So when x is 1, y is 1/2 times 0, so that's 0. So this is the graph. And then when t increases, right? So we're thinking of this curve as the trajectory of x equals t squared, y equals log t. So you see that when t is increasing, both x and y are increasing, and so that means on our curve we are moving in this direction. So as the time is passing, our particle moves along this curve in the direction to the northeast, so to say. And so we have successfully identified our curve and the direction of motion of the particle on it. So unlike for the usual curve, you basically have these two independent characteristics. A, the shape of the trajectory, B, the direction of motion along the trajectory. So we could have put, for comparison, we could have put minus sign in front of both of these two expressions. For comparison, we could have done this. X equals t squared. Let's see. So by replacing t with minus t effectively, so we are thinking of this substitution here, and what this does is it reverses the passage of time. So when t is increasing, minus t obviously is decreasing with the same speed, and so what the substitution does to x is, well, nothing. You have minus t squared, and that's the same as t squared. And here we have log of minus t. And so if in the original equation we had t bigger than 0, now we will have t less than 0. Like so. And so now the trajectory of this on this curve, if you think of it as a trajectory of a physical particle, will be, it has the same shape, right? So if you think of this here as a different parametric curve, it has exact same shape, but now the direction of motion is like this. So as t grows, so think of t as living on the interval from minus infinity to 0. So as t grows from minus infinity to 0, its absolute value becomes smaller, so t squared becomes smaller, and our particle is moving towards the smaller values of x. And similarly, when the negative t gets closer to 0, log of minus t becomes smaller, and so that again corresponds to the direction of decreasing y. So by reversing the t variable, by taking the minus t in place of t, we can reverse the passing of time and make our physical particle move in the opposite direction.